are watching Darasa Online.
Welcome students to our physics period of mechanics. I'm Cyprian Mgina, and today we are going to look at a subtopic of a circular motion, whereby we are just going to look to a section of a motion of a body in a vertical circle. In our last lesson, we had looked at various areas with regard to a motion of a body in a vertical circle, but we didn't preempt all. And today we are just going to look again some more areas which can really be helpful for you to solve the problems with regard to a motion of a body in a vertical circle. But what you are supposed to understand all the time whenever you are interacting with the problems with regard to a motion of a body in a vertical circle is kind of a motion which could just be like this, that we are having a body which is moving in a circle like that. And this body is fixed, let's say this body is fixed to a string. It's a body of a mass m, fixed to a string at the center. So this body is made to move in a circle. And if at an instant this body is at that particular position, describing an angle theta, we all know that there are some two forces which are acting on it. First of all is the weight of that particular body, which is mg. And secondly is the tension force T, which is acting towards the center of the motion. So we can be able to resolve this. We did this in our last lesson, and we can be able to go very quickly. If you resolve along the string here, we are going to have the angle here to be equal to theta, which this will be equal to mg cos theta. Resolving along the circular motion, this will be equal to mg sin theta. Now, if I'm taking the body, let's say, to be moving, let's say, with the velocity v, you could just be able to find that there are some very important points at which this body could be able to reach. There is this point at the top, point A, and this point at the bottom. So we need to know we had already derived the velocity at the top as well as the velocity at the bottom. So if I'm calling this to be equal to VA, and let me call this here to be equal to VB. And we had already known upon that particular velocities at the top and at the bottom. But all in all, there are two ways you can just be able to opt on your own to look, let's say, for the maximum tension of a string whenever a body is moving in such a circle. That whenever it reaches at the top, we could just be able to use even the angle theta, such that the resultant force, which is necessary to keep the body in a circle, the centripetal force, will be equal to the difference of the tension force T minus mg cos theta, which is equal to mv squared over r. And the tension force T at any instant, this will just be equal to mv squared over r, which is the centripetal force, minus mg cos theta. Now the angle theta varies from this position to that position. At this instant, it makes an angle theta to the vertical. So we can be able to look what happens whenever this body is at the bottom. At the bottom, the angle theta is 0. The tension that is developed into the string whenever the body is moving in a vertical circle is given by this particular general expression, such that the tension T will just be equal to that. And for that case, we can be able to determine the tension T at two different positions. At the bottom, that is at point B, and at the top, that is at point A, by using the variation of the angle, as you can be able to see to that particular expression. Such that if we start at a point B, whenever the body M is at a point B, the angle theta there is 0, so that the cosine of angle 0 is 1. So we're just going to have that tension here, the resultant here for the tension at B, as long as the weight is acting downward here. So we're just going to have the T minus mg cos theta, which is equal to mv squared. This is at B. This is at B. So we're going to have at B now instead of a minus, because at B, if we're taking now T, which is equal to mg, T minus mg cos theta is equal to mv squared. So T will be equal to this much plus that much, and the tension at point B will be equal to mv squared plus mg cos theta, but cos theta is equal to cos 0, which is equal to 1. So here will equal plus times mg. So this is the tension. This is the tension at the bottom. And likewise, if we are looking the tension at the top, the mass here, it is still acting downward, but the tension is also acting downward there at a point A, that is at point A. So that the tension at A, we found that the tension at A, which is TA plus mg, then this is just equal to mv squared over r. And actually, if you solve for this, if we solve for this, or if you go back even to the same equation as this, whenever the body is at the top there, the angle theta there is 180. So the cosine of 180 is -1, and therefore, if we are substituting the value for for this particular expression to get the tension at a point A, then this will just be equal to mv squared over r. Now cos theta is cos 180, which is -1, so it will be equal to, instead of plus mg, it will be equal to minus mg. So this will be the tension at the top by using the variation of an angle, and it still makes the tension at the bottom to be maximum and the tension at the top to be minimum. This by using the variation of the angle. But we cannot even be able to use the variation of the angle. We can as well be able to look the direction of the masses of the body whenever it's passing at a point A and it's passing at a point B, such that if we go back and look at this particular point B, the mg is acting downward, the tension is acting upward, and the resultant will be giving us the difference, that is the difference of T at a point B minus mg. This will be giving us the necessary centripetal force to make the body move in a circle. So that we found that the tension at the bottom, that is at point B, is just equal to mv squared over r plus mg, which is the same as an expression number 1 over there. Likewise, if we go to the top, the mg and the tension into the string, they are all acting downward, so that the necessary force to make the body move in a circle, the centripetal force, makes us to have the tension at A plus the mg, because they are moving into the same direction, they will all be equated to the centripetal force, mv squared over r. And if we are looking the value for the tension, if we are looking the value for the tension at that particular point A from that particular expression, this will just be equal to mv squared over r minus mg. And this expression is the same as this expression here, which is the minimum tension in the string whenever a body is passing at the top. So dear students, we have already looked the value for the tension and the variation, and where we can be able to get the maximum tension and the minimum tension. But all in all, we also needed to know about the velocity for the two bodies whenever they are passing at the top or whenever they are passing at the bottom. So the actual force which is really supposed to be maintained by a body, and the velocity to be possessed by a body whenever that particular body moving in a vertical circle is passing at the top, we have already derived in our last lesson that is the velocity v whenever it's passing at the top. The minimum velocity for the body to move at the top without making the string be slack is just equal to the square root of r times g. And the minimum velocity at the bottom, we are calling it to be the minimum velocity, but actually mechanically this is a maximum velocity as compared to the velocity of the same body whenever it's passing at the top. But we are talking about the minimum velocity, which will be able to provide the minimum centripetal force for a body still be able to move in a vertical circle. So this will be the velocity at the bottom, and that is at point B. This is just equal to the square root of 5 times rg. And also, we had already found the velocity at point C, at the horizontal position. The velocity at point C. So whenever a body is passing at a point C, moving in a vertical circle, the minimum velocity at a point C, this is just equal to the square root of 3 times rg. So these are the values which we had already found in our last time.
You are watching Darasa Online.
So let us just go and look the questions I've just prepared so that it could just be able to help you to solve such kind of a problem. The question number 1 says that a stone of 2.5 kilogram is attached to a weightless string of 4 meters length and then moved in a vertical circle from a fixed point which is 8 meters above the ground. If the string does not slack, determine the minimum and the maximum speed of the stone. B. Determine the kinetic energy, potential energy, and the total energy possessed by a stone. C. Determine the minimum speed of the stone when a string is just horizontal. That is our question. So we are having a stone attached to a weightless string and is moved in a vertical circle. If a string is 4 meters long, then it means that the radius of a vertical circle is 4 meters. So we could just have a simple sketch of that particular stone like that, whose radius r is 4 meters, and this stone, the mass of that particular stone is 2.5 kilogram. 2.5 kilogram. And is fixed 8 meters above the ground. So we do take that this point is 8 meters above the ground. So we are taking the ground to be somewhere there. So if the radius is 4 meters, then it means that from the lowest point to the ground there again, that is also 4 meters, because the radius for the length for the string is also 4 meters. So we are having such kind of a body which is made to move in that particular circle. Now we have been given that particular motion doesn't make the string slack. So we need now to solve for part A, to determine the minimum and the maximum speed of the stone. The minimum speed of the stone is obtained at the top. If it's moving that way, here we'll be getting the minimum. That will be getting the minimum speed of the stone, and that particular minimum velocity of the stone is what we have just derived in our last lesson. This minimum velocity, which is obtained at the top, is just equal to the square root of r times g. So it's a matter of just substituting that the radius r is the radius of is equal to the length of the string, which is 4 meters, and the g there it's 9.8. So you calculate it there using your simple calculator and be able to obtain the minimum velocity. And if you calculate there, you will be getting the square root of 39, the square root of 39.2, and if you look for the square root of that, that will be 6.26 meters per second. So this will be the minimum velocity. So the minimum velocity is obtained at the top, and the maximum speed or velocity for this kind of a motion is obtained at the lowest point. At the lowest point. So we are getting here to be the maximum velocity. And this particular maximum velocity, we are taking this to be equal to the square root of 5 times rg. Now it's a matter of just substituting. We are getting 5 times the radius, which is 4 times g, which is 9.8. We look for that particular square root. And this is just equal to 5. That is just equal to 5 times 4, that is 20, times 9.8, which is 196. We look for the square root of 196, which will just be equal to 14. So the maximum velocity at the bottom is just equal to this much. That is part A. Part B, we are going to look for the kinetic energy. and potential energy and the total energy possessed by a stone. So we'll be looking the whole of this energy at the top and the whole of that particular kinetic potential and the total energy at the bottom there. And if we are going to look for the kinetic energy at the top, then let's just look at the kinetic energy at the top. Let me call this to be point A and this to be point B. So the kinetic energy at the top, point A, is just equal to a half times mass times velocity squared. And we all know that, we could be able to substitute here a half times the mass. The mass is 2.5 kilogram. The velocity squared from part A, the velocity squared is 39.2. The velocity v squared is 39.2, and we can just be able to compute it there and be able to obtain this kinetic energy. So we're going to get 49 joules. So this is the kinetic energy. We can look at the potential energy. The potential energy is just equal to mg times h. Now the height from the lowest point of the ground, because this is the ground. The total height, this is 4, and this is 4. So it is 12 meters. So h is 12 meters. And the h is 12 meters. And we are going to substitute here. The mass is 2.5. The g is 9.8. And the height is 12 meters. So from there we can be able to compute and find the potential energy. (294 joules). This is the potential energy. And therefore, the total potential energy plus kinetic energy at the top will be the sum of the two energies. So kinetic energy plus potential energy at the top, this is just equal to 49 plus 294 joules. So we add the two, we are going to get 343. 343 joules. This is the kinetic energy and the potential energy at the top. So we go and look the potential energy and kinetic energy at the bottom. The potential energy and the kinetic energy at the bottom. So this will take us. So here we will just be using the velocity at the bottom. So be using the velocity at the bottom. And that is, let us just first of all look at the kinetic energy at the bottom there. The kinetic energy there, which is equal to a half times m times velocity at point B squared. This will just be equal to a half times the mass is 2.5. And the velocity squared, we are taking the velocity squared is equal to 196. And we could just be able to compute there and be able to obtain the kinetic energy. So here we're going to get 245. The kinetic energy at the top is 245 joules. We're going to look at the potential energy, the potential energy at the bottom. We're talking about the bottom, not at the top. The potential energy at the point B, that's at the bottom. So the potential energy is mgh. But the height there is 4 meters from the ground. So the height there is 4 meters, and therefore the mass is 2.5, the g is 9.8, the height is 4 meters. So we're going to get the potential energy at the bottom, we'll be able to find that here we're having, if we multiply, we're going to get 98 joules. And therefore, whenever we are looking the sum total of the potential energy plus kinetic energy at the bottom, that is at point B, we are taking 245 joules plus 98 joules. Plus 98 joules. So we are having 245 plus 98 joules. We are going to get 343. 343 joules. So you could be able to find that actually there is a conservation of energy, because the potential energy, the potential and the kinetic energy obtained at the top is equal to the potential, the sum total of the potential energy and the kinetic energy at the bottom. There is a conservation of energy. It means that whenever a body is moving up, whenever the body is moving up, it loses the kinetic energy but gains potential energy. But whenever it's moving downward, it loses the potential energy but it gains the kinetic energy. And the total energy at the top will eventually be equal to the total energy at the bottom. And this is what we have already seen to this particular case. That is, the total energy at the top at point A is 343 joules. Also, the total energy at the bottom, that is at point B, is equal to 343 joules. We have already answered part B. So we are going to part C. With this particular case, as long as the body is moving in a circle and it doesn't allow the string to be slack, it means that the actual kinetic energy which will be obtained here is supposed to be the same as the kinetic energy which will be there from the principle of the conservation of energy. And therefore, we could just be able to say that the kinetic energy which is obtained at this particular point, the total energy possessed by the body at this point will be the same as the potential energy possessed by the body whenever it's at this particular point. By that way, it will be moving upward. Let me call this to be the velocity at that particular point C. So we could just be able to find that the kinetic energy, whenever a body is passing at this particular point, plus the potential energy, this will just be the same as the at point B. This will just be the same as the kinetic energy plus the potential energy at a point C. And we can be able to go very quickly deriving this. That the kinetic energy at this particular point, is just equal to a half times mass times velocity squared, plus the potential there, it is mgh at point B, and we'll be able to equate this with the kinetic energy at that particular point, which just be equal to a half mv squared, that is at point C, plus the potential energy mgh at point C. So we can be able to assign now the values of these particular symbols here. The velocity at the minimum point there, as we already said previously, is equal to the square root of 5 rg. So we're having here to be equal to a half times mass times the square root of 5 rg plus mgh. So h, it is this particular 4 meters there. So I'm putting it there, h as it is there. And therefore, this will just be equal to a half times mass m. I'm interested to determine the velocity c squared plus m times g times h. The h at this point is this 4 meters plus that 4 meters. So we can now be able to see. But before we substitute, we are having the m's there, which can just be able to cancel up. And if I multiply by 2 throughout, the m can go. But if I multiply by 2 throughout, then we are having 5 rg. If I square there, and here I'm having 2 times gh, And here I'll be having the velocity vc squared plus g plus 2 times g times h. And if I assign now the values, because I know the value for h at point B is 4 meters, this will just be equal to 4 meters, and I'm not going to take the pure. I just want to get an expression for the velocity at that particular top. So this h here, if this is the radius, which is equal to 4 meters, so this will just be also the same as the radius. So instead of putting h here, the h here will just be the same as the radius. So here we are having 5 rg plus 2gh. The h in our first case here is 4 meters, which is the same as the radius for a circle. So I can be able to put it to 2gr, because h is just equal to the radius. And here will just be equal to, here I'll be having the velocity at c squared plus 2 times g. Now the height at this part here is the same as twice of the radius. So I can take this to be twice of the radius, because twice of the radius is just equal to height h in our second instance, that is at a point, at this particular point C. And if we substitute, if we are just going to look for the velocity at a point C there, then here I'm going to have 7 gr, and here it is 4 gr. That this, I'll be taking this minus this. That is 4 times gr. 2 times 2 is 4 gr. And if we take the substitution here, this is equal to 3 gr. So the velocity c will be equal to the square root of 3 times g times r. So this is the minimum velocity of the stone whenever the string is just horizontal. And we can be able to substitute the values and be able to get the final answer. If we substitute the values, we know the g is 9.8, and the radius in our case here is 4 meters. So we take the square root of that, and we can be able to compute, of which we are just going to get 3 times 9.8 times 4. We take the square root of 117.6, which is equal to 10.84. So this is the velocity of this particular body whenever it's just passing at point C.
You are watching Darasa Online.
Okay, students, let's go to the second question. Goes like this. A ball of 2.5 kilogram is swung in a vertical circle using an extensible string of 2 meters long, fixed at a point 6 meters above the platform. If the string breaks when a maximum tension is reached, determine A, the angular velocity of a ball as it passes at the lowest point of a circle. B, the kinetic energy and potential energy of a ball at the lowest point. C, the maximum tension the time of flight, and the range of a ball if the string breaks at the moment it passes at the lowest point. So we are having the same sketch as the previous one, but it's a different question. So we are having such kind of a body which is rotated in such a circle. And that particular body, we are taking the mass of that particular body is 2.5 kilogram, and the radius of the vertical circle is 2 meters. So it's being rotated from that particular point O, which is 6 meters above the platform. So we are taking the platform or ground to be somewhere there. So this is the ground, or more or less we are saying to be a platform. And then we are being asked to determine the angular velocity of a ball as it passes at the lowest point of a circle. The angular velocity. So that is part A. going to determine the angular velocity. Now I don't need to derive some other formulas of which we have already derived previously and even in our previous lesson. So if the ball is moving, let's say in anti-clockwise that way, whenever it's passing at the bottom here, it will be able to possess a certain velocity. Let me call this to be equal to VB. Okay, at the top it will be possessing a velocity VA. So whenever it passes at the bottom, we need to determine its angular velocity whenever it passes at the lowest point. And this velocity, at that particular point, we had said that's equal to, will just be equal to 5 times G times R, okay? That particular velocity will just be equal to that much. And of which we could just be able to compute. Computing for that particular velocity, then we're just going to have the 5 times G times R, where G is 9.8. And the radius there is 2 meters. So we're looking for the square root of that. We're looking for the square root of that. And we could just be able to compute, which is equal to 5 times 9.8 times 2. We're going to get 98. So we're looking the square root of that, which is 9.899. 9.899 meters per second. This is the velocity. But we had been asked to determine the angular velocity. We know that V is just equal to R omega, where omega is the angular velocity. So the omega there will just be equal to V over R. And the velocity is the one we have just obtained there, which is 9.899. So we divide with R, which is 2 meters, to get the angular velocity. So that particular answer we divide by the radius, which is 2 meters, to obtain the angular velocity omega, which is 4.949. 4.949. And this is angular velocity, which is measured in radians per second. So our angular velocity will be 4.949, which is measured in radians per second. So that is part A. Part B, we are looking for the kinetic energy and the potential energy of a ball at the lowest point. So as we have done in our previous question, it's not supposed to take us more time, because it's more or less similar with the one part of our previous question. That the kinetic energy just be equal to a half times mass times velocity squared, and we are just going to substitute, which is a half. The mass there is 2.5, velocity squared, this will just be equal to 98 from what we have obtained above there. So this will give us the kinetic energy. That is 98 times 2.5, which will just be equal to 122.5. And we can be able to determine even the potential energy. The potential energy. The mass is 2.5 kg. The G is 9.8. And the height, remember, this is 6 meters from the bottom. So if the radius is 2, then this will be equal to 4 meters from that point. So the potential energy will depend upon this height of 4 meters. So we multiply by a 4 to get the potential energy. So we are taking 4 times 9.8 times 2.5. We are just going to get 98. So the potential energy obtained, that is 98 joules. So this is kinetic energy, and the potential energy of that particular ball at the lowest point. So part C, the last part, we are looking the maximum tension and the time of flight and the range of the ball if the string breaks up at the moment it passes at the lowest point. So the maximum tension, as we already said previously, is obtained whenever the body passes at the lowest point. So the tension obtained at that particular moment is the maximum tension. And this maximum tension is just equal to mv squared over r plus mg. That maximum tension just be equal to this much. So we need just to determine this maximum tension. If we substitute, we take m outside, we're getting v squared over r plus g. So if we substitute, the mass is 2.5 and the velocity at the bottom, sorry, I've just rubbed. The velocity at the bottom is equal to the square root of 5 rg, which is equal to 5 times 2 times 9.8. We are taking the square root of that. That is 5 times 2, the radius is 2, times 9.8, which is 98. The square root of this will be equal to 98. So we're taking this to be equal to 98 over the radius. Again, this is the radius, there is 2. So plus g, which is 9.8. And if we compute it there, then we are getting something like this. So here we're going to get 49 plus 9.8. We are getting 2.5 times 58.8. So if we multiply there to get the last answer, we are going to get 147. So the maximum tension, that will just be equal to 147 newtons. So the maximum tension which is obtained at the bottom is 147 newtons. So that is that answers the maximum tension.
You are watching Darasa Online.
Now we had been looking the time of flight and the range. If the string breaks at the moment that particular ball passes at the bottom. So it means what? It means that whenever the ball passes at this particular part, it can be able to break. Whenever it breaks, then it will just be like a horizontal projection. And that particular horizontal projection will take the body in a parabolic path, whereby the body will come and land to a ground at this point. So the range we are supposed to determine, it is this distance, the horizontal distance from the actual point just below the point where this particular string have just broken. And we need to determine also the time of flight from this point until when it lands to the ground or a platform. So we really need now just to apply the theory of a projectile motion, which is not difficult. That first of all, we need to determine the time of flight. The time of flight will just will be depending upon this particular equation, which will just be equal to y plus h plus v naught sin theta times t, v naught sin theta times t minus a half times gt squared. But taking the time of flight, we put it to be equal to 0, which is equal to h plus v naught sin theta times t minus a half times gt squared. But remember, if the initial velocity of projection is horizontal, the angle of projection here will be equal to 0. And therefore, talking about sin 0, the sine 0 will be equal to 0. And so the whole of this particular expression doesn't exist. And what we're going to have here is that the a half times gt squared, this will just be equal to h from that particular expression. So that the time of flight t will just be equal to 2h over g, the square root of that. So this will be giving us the time of flight. And we can be able to substitute and obtain the time of flight. The height h is the distance from that point to this point, which is equal to 4 meters. And we all know what is g. So here we'll be getting 2 times 4, 2 times h, which is 4 meters, over g, which is 9.8. We look for that particular square root. This is 8 over 9.8. We look for that particular square root. It's the square root of 0.81. Square root of 0.8163. And if we look at the square root for that, we're going to get 0.9. 0.903. 0.9035. So this is the time of flight. So the time of flight will be almost 0.9 second. Having known or obtained the time of flight, if we need to time the range can just be obtained by taking the horizontal component velocity times time of flight. So the range r will be obtained by taking the horizontal component velocity times the time of flight. The horizontal component velocity is v naught cos theta times the time of flight. So the v naught cos theta is cos 0. Cos 0 is 1. Okay? Cos 0 is 1. So here we'll be taking a v naught times t. The time of flight is that one, and the v naught is the velocity reached by the body at the lowest point there. That particular velocity, the minimum velocity obtained at the lowest point there, is just equal to this much, which were 98, I remember. 9.8 times 2 times 5. Yes, this the v squared was just equal to 98. So taking the velocity v, we are taking the square root of that. The square root of that is 9.899. That is the velocity, 9.899, okay? 9.89949. This is the velocity in meters per second. So if we multiply, then we are just going to get 8.944. These are meters. That is the range from this point to that point. So it answers the last part. That is the range of the ball whenever the string breaks and the body moves horizontally from that point, it lands to the ground, covering such a distance r, of which we have already determined it to be equal to 8.9 meters, almost 9 meters.
You are watching Darasa Online.
Okay, students, that takes us to our last part, but I believe you can just be able to solve many problems which could just be very similar to this or with some other questions, but all those formulas which you have just learned in our previous lesson and as well in this lesson, all of them are just very helpful for you to solve them. But remember, these problems with regard to the motion in a vertical circle are not difficult. What you can be able to remember that this particular vertical motion is not a uniform motion. It keeps on changing because of the gravitational force which supports the motion whenever the body moves downwards and opposes the motion whenever the body is moving on its way upward. So that particular motion is not uniform. For that particular case, you will be able to find that forces do change. And if you'll be able to remember all of this, and remembering all of the formulas we have just learned and derived previously, then it could just be able to take you to a very new level of understanding, solving this kind of problems. Okay, we're going to have a short break, and whenever we come back again, I'll be able to share with you some particular questions, and you could be able to take that particular question as a homework for you to do it at home.
You are watching Darasa Online.
Okay, students, we are back again, and the question for you is this one here. A certain road has constructed such that it has a long hump forming an arc of a radius of 40 meters. What is the maximum speed with which a car can be driven over it without leaving contact with the ground? This is a very good question, such that if I'm taking a ground, something like that. Now, I'm taking this to be as an arc, such that if we extrapolate the whole of this particular arc, it will be a very big circle, whose radius from the center there is the one which is given there, that is 40 meters. Now, a car is being driven over that particular arc. Now, the speed of a car, if it's really very big, it will find that whenever it reaches to a certain point, it will just be able to leave a contact with the tarmac road, or with the road there, or with the ground. Now, we are being asked to determine the maximum speed, that it should never be the maximum speed at which this particular car should be driven without leaving contact with the ground. It should be able to maintain in contact with the ground. That is the one which is really necessary for you to understand. That whenever a car is moving in that way, not living in contact with the ground, it will be possessing a particular centripetal force. A particular centripetal force, which is just equal to mv squared over r. Now, that centripetal force is the one which is really very important for you to understand, of which it will be helpful for you to find the maximum speed at which this particular car will be driven without leaving contact with the ground. So that is just a hint. So try to go brainstorm with whatever we have just learned here, and I hope you can be able to reach to the final answer. Thank you, students, for today, and I believe next time whenever you are facing problems like this, it will be much easier for you to solve. Thank you. See you next time.